Hi there, this is Truth Socrates and welcome to today's video where we will be talking about improper integrals. Now, when you hear the word improper, you're probably thinking, well, something must be wrong with it because it's not proper. Well, of course, that is a technical term, and we are going to see that there are two ways by which an integral might have something which is a little bit fishy, something a little bit wrong with it. So the first type of integral is where the domain of the integral is infinite. Okay, so in other words, it's something like closed on the left of a and going all the way to the right to positive infinity. So the integral looks like this. We're going from a number a to positive infinity. And as usual, we're going to require that our function is continuous on the domain from a to infinity. Okay, so at least there's that minimum requirement. So we will say that this definite or improper integral converges to the number L, and we will simply write it as an equation that the integral from a to infinity of f of x dx is equal to L. If the limit as b approaches infinity, where b is the upper limit of the integral of our function, in other words, we're only integrating from a to b, our f of x dx, if the limit of this definite integral, which is now a proper integral, is some number L. Now, of course, a limit does not always exist. And we saw when we learned about L'Hopital's rule, especially, that lots of weird things can happen. Okay, so if the limit is L, great, but there are also a couple of other possibilities. Maybe the limit as b approaches infinity of this integral is infinite. Okay, and we're going to see examples where that does happen. In that case, we'll say that our function diverges to infinity. And maybe the limit is negative infinity. So we'll say that the integral diverges to negative infinity. Okay? Now, it's also possible that this limit simply does not exist, in which case we say that the improper integral from a to the infinity diverges. We don't say diverges to infinity, we'll just say diverges. It's bad, really bad. So, similarly, you might have a lower limit of negative infinity. All right? So you can certainly rewrite everything that we did up here to apply to this scenario. Okay, so this time we replace the lower limit with a, and we make a approach negative infinity. Okay, oh, by the way, in case you're wondering where am I, yeah, this is not my home office, this is my school office, and yes, that is Mr. Superman way up there. All right, so let's take a look at some improper integrals. All right, so for these 5 improper integrals, our domain will be from 1 to infinity. Okay, so we will look at 4 functions and this general kind of function. They kind of all have the same form, right? We have 1 over x squared, 1 over x, 1 to the square root of x, and 1 over x to the 3 halves. So they all look like 1 over x to a power p, which is a positive power. Okay, 2, 1, 1/2, 3 halves. Okay, and you might say, well, what about negative 2? Well, what about 1 over x to the minus 2? Isn't that just x squared? Okay, so if the exponent is negative, we put it in the numerator as a positive power. And then we're going from 1 to infinity. Well, x squared, the antiderivative is x cubed over 3. As x goes to infinity, x cubed goes to infinity. So that has absolutely no hope of converging. Okay, so it would diverge to infinity. Okay, these functions have some hope of converging. Okay, so let's take a look at the first one. Okay, so we have 1 over x squared, integral from 1 to infinity. So that's x to the negative 2. So add 1, x to the negative 1 divided by negative 1. So we have negative 1 over x as our antiderivative. Okay? And we're taking the limit from 1 to b. Okay, so yeah, let's put that step in. Okay, before we do the antiderivative. So this is the limit as b approaches. Where's my arrow? There you go. As b approaches infinity. Where's my infinity? There. Oops. Yeah, there you are. So we're integrating from 1 to b. Okay, so we can't plug in infinity because infinity is not a number. So we need to find this limit. Okay, so we'll do that again over here once we take the antiderivative. So we are evaluating from 1 to b. Okay, so in the upper limit we have negative 1 over b, and then minus minus plus 1 over 1. Okay, and we are still taking the limit. And maybe I should scoot out of the way here. So we take the limit as b approaches infinity of minus 1 over b plus 1 over 1. So of course, as b gets bigger and bigger, negative 1 over b gets smaller and smaller. Okay, so the limit is 0. We get 0 plus 1, or simply 1. Okay, so we will say that this integral converges to 1, or we simply say that integral equals 1. Okay, so that converges. Okay, so now that we see that idea, yeah, maybe they'll all fit in here. Okay, so we take a limit as b approaches infinity. Same format, but we now have 1 over x dx. Okay, but of course that integral, the antiderivative, the power rule does not apply. I hope you remember that this should be an ln. ln absolute value, but we're on a positive domain, so we'll skip the absolute value. So that's the limit of ln of x as x goes from 1 to b. Okay, so I can copy these limits. Haha. Okay, so now we need ln of b minus ln of 1. Okay, so ln of b minus ln of 1. ln of 1 is just 0, so that's the easy part. What happens as b approaches infinity of ln of b? Okay, so remember how ln of x looks like. It's concave down, but it goes to infinity. Okay, it keeps going higher and higher without bound. So this goes to positive infinity. Okay, so we will say that this improper integral diverges to positive infinity. Okay. So, yeah, you know what? Let's take a look in GeoGebra, because you might say, well, wait a minute, these look alike. How come one of them converges and one of them diverges to plus infinity? How does that happen? Let's go to GeoGebra. All right, here we are. And we were working with 1 over x squared. So GeoGebra can do an integral for us. Integral of 1 over x squared. And let's go from 1 to 10. Okay, 10 is far, far, far from infinity. But, okay, so check it out. If you only go from 1 to 10, the integral is 0.9. Okay? If you increase 10 to 100, we won't see the right endpoint, but, oh yeah, there it is. Okay, so it still says it over here. It's kind of off the screen here. It's now 0.99. Okay, if you want to see more of the screen, we can change the proportion. So we want to squish the x-axis. So we want to go, how about 10 to 1? Yeah, there you go, squished. Okay, so we can see up to 100. So of course, 1 over x squared is getting very, very close to the x-axis. So that definite integral is 0.99. Okay, and of course, if you add another 0, yeah, forget it. It's going to be way off the chart, so to speak. Yeah, it's now approximately 1 because I'm only accurate up to 2 decimal places. Okay, of course, if we add more decimal places, we'll see it's more like 0.9999999, and so on. Okay, so of course we see that in our limit because we had negative 1 over b. Okay, so negative 1 over 1,000 subtracted from 1. Yeah, you will get 0.999 or whatnot. Okay, so what happens if we change the x squared to x? Okay, so very different antiderivative. It's now ln of x, but GeoGebra will do it automatically for us. Okay, I want to get rid of that exponent altogether. So 1 over x, and ooh, you don't see the message. Haha. Okay, 1 to 10. Yeah, ooh, it's 2.3. Okay, that's bigger than 0.99. What if we go to 100? 4.61. So it more than doubled. Okay, which is not horrible. But how about 1,000? Ooh, 6.91. Yeah. So the point here, of course, is that, yeah, the ln function grows very, very slowly. Okay, but of course it's, yeah, you should be a little bit worried now. Okay, it's not slowing down. It keeps, yeah, it's jumping. Okay, so, yeah, of course we know because of our knowledge of the ln function that ln of x will go to infinity. Okay, so we can play this game until the cows come home. Yeah, we'll keep getting bigger and bigger numbers, but our actual knowledge tells us that our limit for ln of x will be positive infinity. Right, back to our list over here. So this time we'll have 1 over square root of x. That is x to the negative 1/2. Negative half plus 1 is positive 1/2. So our antiderivative is x to the positive 1/2 divided by positive 1/2. Did you get all of that? So that is 2x to the positive 1/2. Oh no, I forgot the limit symbol. Okay, so let me give you a little shortcut. If you want to save some time, cheat a little bit, we will simply put the infinity symbol as part of our antiderivative or part of our definite integral. Okay, so of course that looks kind of weird, right? But of course it means something. Okay, so it means, of course, that we're taking a limit, even though we're not including the symbol b or the word lim for limit in this equation. Okay, so what you simply have to think of is that the upper limit is getting bigger and bigger. Okay, so that is what that infinity should tell you. Okay, we're plugging in a number bigger and bigger into x to the 1/2. Okay, well, we know x to the 1/2, that's just square root of x. We know that that will definitely go to positive infinity. Okay, 1 to the 1/2, of course, that is just 1. So our limit is positive infinity. And if you want to look ridiculous, then you will subtract 2. And of course, that is just positive infinity. Okay, so both of these go to diverge. Both of these diverge to positive infinity. Okay, one more. X to the 1 over x to the 3/2, so x to the negative 3/2. Okay, so we had 1/2 here, x to the negative 1/2. This is x to the negative 3/2. So negative 3/2 plus 1 is negative 1/2. So x to the negative 1/2 over negative 1/2. So we have negative 2 x to the power negative 1/2. Okay. So again, from 1 to infinity, I already have these here, so I can recycle those. And again, the easy part, at 1, it is 1 to the minus 1/2, so that is still 1. And so you have minus minus plus 2, okay? But at infinity, okay, so we have x to the negative 1/2 this time. So it's not positive 1/2, it's negative 1/2. It will be decreasing down to 0. getting a limit of 0. Okay, so we have 0 minus minus 2, so it's going to be plus 2. Okay, so our definite integral or improper integral this time converges to 2. Okay, so yeah, we have two examples where our definite integral converges, but 2 where it diverges. Okay, so we want to know now, in general, when will 1 over x to the p converge? And of course, opposite question, when will it diverge? And it looks like it's going to diverge to plus infinity. Will it ever diverge, period? I don't think so. Let's see. All right, so let's think about this. When will the improper integral from 1 to infinity of 1 over x to the p dx converge? When will it diverge? So we already saw that when p equals 1, it diverges. And here, p equals 2, it converges. P equals 3/2, it converges. P equals 1/2, it also diverges. Okay, so it looks like 1 is possibly the magic number. Okay, when the power is 1, it diverges, and anything below 1, 1/2 is below 1, smaller than 1, the integral also diverges. Okay, but 3/2 is bigger than 1, 2 is bigger than 1. Okay, so it looks like 1 is the magic number. Okay, so let's think about the antiderivative. Okay, it's x to the negative p. So by the power rule, the improper the antiderivative is x to the minus p plus 1 divided by minus p plus 1. Okay. And the point here is that you want a limit of 0. Okay, just like we saw over here. We don't like limits of infinity. Okay, that's bad, 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 bad. So the way to get a limit of 0 is, in this case, where the exponent is negative, which means that we'll bring it down to the denominator. Okay, so what that really means is we can keep minus p plus 1 down here. Let's wrap it in parentheses, but we'll bring the x to the denominator. So negative p plus 1 becomes positive p minus 1. Haha. So this now becomes 1. And now we see that if p is bigger than 1, then this exponent is positive, which means that the x will stay in the denominator. And as x goes to plus infinity, 1 over x to the p minus 1 goes to 0. Yay! All right. And conversely, if p is smaller than 1, then p minus 1 will be negative, so it belongs in the numerator, right? So it will have a positive exponent in the numerator, and that's when we get a limit of positive infinity, when x stays in the numerator. It's there in the numerator, there it's in the denominator. Okay, so when does this converge? When p is bigger than 1. Yay! So these are called p integrals for obvious reasons, and we will see them in a few videos actually when we start up on our study of infinite sequences and series. They are very important when we look at what are called p-series, p-integral, p-series, and we'll see that our p-series converge, same word, when p is bigger than 1, and diverge when p is smaller than 1. So now we're going to look at the second kind of integral. It's where the function has a point of discontinuity in the domain, and this time it'll be from a to b, wherein they're just ordinary real numbers, just like what we've seen up to this point. No infinity in our domain. Okay, so to introduce this new kind of improper integral, we will consider the case where there is a vertical asymptote, for example, or more generally a point of discontinuity at x equals a, the left endpoint. Okay, so once again, we will say that this improper integral converges to a number L, and we will write it as simply this integral equals L, if this time the limit as c approaches a from the right of the integral from c to b of our function is this limit L. Okay, so yeah, we're approaching A is your left endpoint, so we can only approach it from the right. Okay, so we are integrating from C to B, where C is approaching A from the right. So similarly, if you have a vertical asymptote at x equals b, then you can only approach b from the left, and you'll take a limit as c approaches b from the left of integral from a to c this time. Okay, now if the point of discontinuity is somewhere between a and b, then what you'll have to do is you'll have to split it up into two parts, and then you have to find a limit for each of those parts. Okay, here we go. New examples. What? New examples? Aren't they the same as before? No, because this time we are going from 0 to 1. Okay, so 0 is bad for all of these functions because we don't want to divide by 0, like ever. But we can take limits. Okay, so again, let's start with the proper notation. Okay, we are integrating from 0 to 1, but 0 is a bad point. So we will want to take the limit as c approaches, where's my arrow? C approaches 0 from the right. That should be a superscript. Oops, sorry. There you go. Approach 0 from the right. Of, why do I keep getting an arrow there? Okay, there we go. So we have an integral from c to 1 of 1 over x squared dx. Okay, so same antiderivative, x to the minus 2, so x to the minus 1 over minus 1, so negative 1 over x. Okay, so we have the antiderivative, and it is negative 1 over x, and we are integrating from c to 1. So, oops, excuse me more, and down there, c, oops, I'll get there, c to 1. Okay, so we are going to get the limit as c approaches 0 from the right. So at the upper limit, we have negative 1 over 1, so that's simply negative 1. And then we have minus 1 over x, so it's going to be plus 1 over x. But we have c. Okay, so this time we're not going to infinity. C is going to 0 from the right. Okay, so through positive values. Okay, and that's important because 1 over c has different limits from the left or the right of 0. We are approaching from the right of 0, so it means that this will have limit of positive infinity. So we're going to have negative 1 plus infinity. So of course that means that our integral will diverge positive infinity. Okay, so yeah, if you want to scroll back, this was 1 to infinity, this converged. It converged to, was it 1 or something? Yeah, but now it diverges to plus infinity. What about 1 over x dx? Okay, so yeah, let's do the shortcut. Okay, so instead of writing limit, we will jump to the antiderivative. We will have ln of x as our antiderivative, and of course we're going from 0 to 1. So yeah, no more c, no more limit symbol. We'll go from 0 to 1. Okay, ln of 1, that's not a problem, but ln of 0, ooh, so that's where now we're actually thinking. Okay, it's not literally ln of 0, it's ln of x as x approaches 0 from the right. Okay, so I'm using the same letter, x. Why use c when we have a perfectly good letter x here? So ln of x as x approaches 0 from the right. So that's going to be negative infinity. Okay, so remember the graph of the ln function. You have a vertical asymptote at x equals 0. You're approaching negative infinity as you approach 0 from the right. So this is going to be minus of minus infinity. So of course, that is bad news. That is 1, 0 plus infinity. So simply infinity. Okay, so yeah, still bad. Okay, so whether you're going from 1 to infinity or 0 to 1, sorry, 1 over x, it's just not your day. Okay, 1 over square root of x. X to the minus 1/2, add 1, you get x to the plus 1/2, divided by plus 1/2, so that's 2. X to the plus 1/2. And we are going from 0 to 1. Okay, so when x is 1, we simply get 2. As x approaches 0, x to the 1/2 square root of x, that's not an issue at all. Okay, so that has limit 0 just by direct substitution. So we get 2 minus 0, which is 2. So this time 1 over square root of x converges if we integrate from 0, 1. Okay, so that kind of makes sense. Before, this was good from 1 to infinity, and this was bad from 1 to infinity. Okay, so this time they switch roles. So, good or bad? It should be, it's on the same side of 1 as 2, so it should be bad. Okay, so let's see. So we said x minus 3/2 plus 1 minus 1/2. So x to the minus 1/2 over minus 1/2. So that is minus 2 x to the minus 1/2. Okay, going from 0 to 1. So at 1, no problem, we get negative 2. But at 0, so again, we're taking a limit. We have x to the minus 1/2, which is 1 over x to the 1/2. So as x approaches 0 from the right, that is going to positive infinity. Minus negative 2, so that's plus 2 times positive infinity. Okay, so of course, twice infinity, still bad. So, yep, this improper integral also diverges to infinity, like its next door neighbor, 1 over x squared. Right, let's do something very different. Okay, well, not so very. We're still going to 0 and stopping at 1, but no more 1 over x to the p. Well, sort of, but now we have our friend ln of x over here as part of the integral. Okay, so what technique of integration do you think we can use to find an antiderivative for this thingy over here? Did you guess integration by parts? In that case, you would be correct. What would be the parts? How about, okay, so we need something that will differentiate nicely and something else that integrates nicely. I don't like the integral of ln of x, do you? I don't think so. So that will be our u, and our dv will be the 1 over square root of x dx. Don't you think that's a good idea? Okay, so that'll be a 1. And our du, of course, is 1 over x. Okay, so let me borrow that. 1 over x dx. All right, and now, oh, we were just integrating 1 over square root of x dx, right? So one more time, because my short-term memory. X to the minus 1/2 plus 1, okay, plus 1/2, so x to the 1/2 over 1/2, so that's 2x to the 1/2. 2x to the 1/2. Why are you there? 2x to the 1/2 dx. Okay, there you go. So our antiderivative of ln of x over square root of x dx will be, how odd, will be u times v, so it's ln of x times v. And it looks like this looks, I'm sorry, there should be no dx anymore. We integrated. So 2x to the 1/2 ln of x minus integral of v du. Okay, so we want the integral of v, 2x to the 1/2. du is 1 over x dx. Okay, that's good. So you know what, let me put it on the next line over here. And oh, now I see why that was doing it. Okay, there we go. That looks better now. Okay, so what's going on here? Oh, that's easy. X to the 1/2 times 1 over x. So that is 1 over x to, well, just keep it as x to the negative 1/2. Okay, because we still have to integrate it. So plus 1, here we go again. We have 1/2. And we have x to the 1/2 over 1/2, so 2. Okay, so it is negative 4. Yeah, let's bring the 2 up. And then we have 2x to the positive 1/2. Okay, so that is now just minus 4 x to the 1/2. Okay, not feeling very confident. Are you correct? Let's see. Am I right? 2 square root of x ln of x. All right, 2x to the 1/2 ln minus 4 square root of x. Thank you, Maple. All right. So we have the correct antiderivative, and now we have to plug in the limits. Okay, so let's bring back our problem. What's your problem? It's over here, and we are ready to plug in 0 and 1. Will we get a limit? 0 and 1. Uh-oh. I don't like this. Just kidding. So we're going from 0 to 1. Okay, let's start with 1. Okay, because, maybe we should have started with that. The issue here, of course, is 0 still. Okay, just like before. Okay, so maybe you caught that right away. Is there an issue at 1? No, ln of 1 is 0, no problem. Square root of 1, 0 over 1, 0. So no problem. Okay, so is 1 now an issue at the antiderivative? Well, let's see. We have 2, 1 to the 1/2 is just 2. Oh wait, but ln of 1 is 0. Minus 4, 1 to the 1/2, that's just 1. So that's minus 4. Okay. And then we're approaching 0. So the x to the 1/2, that's no issue. That's just going to 0. But we have x to the 1/2 ln of x. Okay, so yeah, I'm not too crazy about this. Ln of 0, no. We're approaching 0 from the right. We're going to negative infinity. But we have 0 to the 1/2, 0. Ooh. So a few videos ago, yeah, we had L'Hopital's rule where we can find this limit. It's a 0 times infinity limit. Okay, so let's highlight that, because slow down a little bit, is an indeterminate form of 0 times negative infinity. minus infinity. Of course, as x approaches 0 from the right. Okay, so that's bad. But we know how to use L'Hopital's rule. Okay, so we will turn that product into a quotient. We will flip one of those factors into the denominator. And yeah, so this one, just so you know, this is to be continued. Okay, so we will flip one of those factors into the denominator, and ln of x is never a good idea to flip that into the denominator. It's going to be nasty. So we flip the x to the minus 1/2. It becomes x to the minus 1/2. So now it's a 0 over 0 form. So we can apply L'Hopital's rule. Derivative of ln of x is 1 over x. Derivative of x to the minus 1/2 is negative 1/2 times x to the minus 3/2. Minus 1/2 minus 1 is minus 3/2. So what have we got here? Negative 1/2 flips over, becomes negative 2. X to the minus 3/2 flips over, x to the positive 3/2 divided by x, so that's x to the positive 1/2. Okay, so as x goes to 0, wonderful, this has limit of 0. Okay, so that's nice. So we can't just plug in 0 here. We need to take this limit responsibly. Okay, this one is limit 0. So it is just negative 4. And to emphasize, it is minus negative 4 minus 0 minus 0. Okay, just so you see where those came from using L'Hopital's rule. LH. All right. Okay, and I just checked with Scientific Notebook just in case I messed up. We can use this and it will tell us, yep, our improper integral does converge to negative 4. Yay! All right, so for our final example, we are going to look at the hybrid sort of integral. So we have integral from 0 to infinity. So infinity, it is sort of like a type 1 integral. But we're also starting at 0, not 1. Okay, and that's bad for this guy because square root of 0 is 0. So we have a vertical asymptote also at x equals 0. Okay, so when that happens, technically you're supposed to break it up into 2 pieces. Okay, so that will be computed as 2 terms. Integral from 0 to 1 of that thing, and then from 1 to infinity. So break it up somewhere in the middle, and 1 is good enough. Okay, you might say, well, I like e or square root of 7. Oh yeah, you're weird. 1 is a perfectly good number. You can break it up at 2, sure. Maybe at the end we'll find out, well, what happens if you change 1 to something else? Okay, so of course the main problem right now is, well, how do you get the antiderivative of this thing? We're going to need it in both integrals. Okay, so we want to know what is the integral of 1 over radical x, x plus 1 dx. Okay, so what is that antiderivative? Okay, so integration by parts, maybe not. So how about just a u sub? Okay, maybe you recognize this. We did some examples like this earlier. Okay, yeah, so just let u be equal to x, square root of x. Let u be square root of x. So du is, oh, well, actually, so x equals u squared, and dx is 2u du. Okay, that's better than getting dx from du from here. Like, it's much nicer, don't you think? Okay, but, okay, so gotcha. We got dx, but how about x plus 1? Okay, so here we go. So, and x plus 1 is u squared plus 1. Ooh, ooh, u squared plus 1. Ooh. Okay, so we have all the ingredients that we need. So this is gonna be, by substitution, our square root of x is our u, and then our x plus 1 is u squared plus 1. Our dx is 2u du. Okay, so that is just wonderful because the u's cancel. Yay! So it's 2 over u squared plus 1 du. Okay, remember this? So this antiderivative is the arctan function. Ooh, it makes an appearance. Oops. 2 arctan of u. All right, there we go. So that is our antiderivative. So we can go back here and plug in our endpoints. Okay, so let's see. For our first integral, we have 2 arctan u, and we're going from 0 to 1. Okay, so I'm skipping the limit symbol. Okay, and then for our second one, we are going from 1 to infinity. Infinity over here. Okay, so do these limits exist? Okay, so we had an issue at 0 because we don't like to divide by 0. But arctangent of 0, that's not a big issue, is it? Okay, so, well, don't forget we start at 1. So we have 2 arctangent 1. And that's actually a nice number, right? That's pi over 4. Okay, excellent. However, we want minus 2 arctan 0. We can do it by direct substitution because that's just 0. But there's more. So we have 2 arctan u. As u goes to infinity, we start with the upper bound of infinity. Okay, arctangent infinity. So it's not literally arctangent infinity. We are getting arctangent of u as u gets bigger and bigger, as u gets closer to infinity. Okay, so hang on. My bad. I forgot to change limits, but am I saved? When when x is 0, u is 0, so that's nice. And when x is 1, u is 1. Okay, so far so good. And then when x is infinity, square root of infinity, still infinity. Okay, phew. Okay, so that works. But, so back where I got distracted and panicked. As u goes to infinity, 2 arctangent u. Remember that one? Arctangent has horizontal asymptote. As you go to the right, that horizontal asymptote is, remember, pi over 2. Ooh, 2 times pi over 2. And then we still have the minus 2 arctangent 1. Okay, so I mentioned earlier, okay, so can you replace this with square root of 7 or anything weird like that? Yeah, sure. You can replace this number with any number c, which is between 0 and infinity. In other words, just an ordinary positive number. And you will go from 0 to c, so you will have arctangent c over here, and you'll have arctangent c over here. So notice that one of them is positive, one of them is negative. So it doesn't matter where you cut up, subdivide your domain, the two c's are just going to cancel each other out. Okay, so what is important is the 0 and the 1. So even though arctangent 1 is pi over 4, that's fine because it's just going to cancel out anyway. All right, so arctangent of 0 is 0, 2 times pi over 2, we just get pi. All right. So, wow, not even 1 hour today, and that's just good because thinking about pie is making me hungry and it's about lunchtime. So, I hope you enjoyed that video, and until next time, enjoy the rest of your day. Bye.